In this lesson, we're going to learn about the ideal gas law, which is a law that kind of combines a bunch of different gas laws that we'll all see put together here. So some of these other laws, you can see Avogadro's law, Boyle's law, Charles' law. These are laws that kind of relate some of these pressures and volumes and mole amounts and temperatures. So these four actually can be sort of rearranged. These four variables can be rearranged and made into something called the ideal gas law, which is represented here. So this is formula of PV equals nRT. Now, you should hopefully recognize a few parts of this. P, for example, that's pressure. V is volume. N, this is the mole amount of the gas in question. R, I'm going to skip for a second because I'm going to go to T. T is temperature, and of course T must be done in Kelvin. Where the only thing that we haven't learned about here is this R. R is something called a universal gas constant, and very often I'll just say the gas constant. But this is a gas constant that kind of makes these four variables come together. It's a number that's always going to stay the same in any context. And over here on the right side, they give you a little table for values of R. And I hope you're not too intimidated by this one. Actually, you only need to know one of them. But I want to show you the difference between them. So right now you have a value of R and a corresponding unit of R. So you see right here, this is going to be some value, 0.08, whatever, some 8.31, 62.4. So it looks like there's three different values. And the important thing to recognize is that these units of R correspond to that value, but the difference between them really is almost just one thing. So if you look at them, let's go ahead and highlight this. Right, the only thing that really is different between them is this part right here in the top right. Well, if you look carefully, right, ATM, KPA, mmHg, what is that? Those are units of pressure. And so the only difference between these three values is really the units of pressure that you would apply. So either way, the important one that you'll have to know then is going to be this one. I just want to show you the other ones because those are sometimes ones you might come across, but the most important one by far is this first one. And of course, just kind of clarify exactly what you need to know. This is a value you want to memorize, and I'm also going to change it just a little bit. But go ahead and memorize this one, 0.08206, right? So instead of 21, it gets 206. This is one that's more appropriate, and then that's going to be in units of liters, atmospheres per mole K, all one set of units. All those are there. So go and commit that one to memory because that's going to be a gas constant that we'll use for a lot of this, and it'll become handy later. We've briefly talked about this before. What makes a gas ideal is that they're kind of a theoretical concept, ideal gases, that perfectly follow the kinetic molecular theory, where if you remember, right, all particles are really tiny, their volume is negligible, there's little to no intermolecular forces, all the collisions are elastic. And again, as you can imagine, that's an ideal gas. In reality, not all gases quite follow that perfectly, but this one again does a pretty good job of more or less representing every gas. And that's this sort of made-up ideal gas. And we assume that pretty much all gases behave ideally. The only time we don't see this is when you have high temperatures and low pressures. And that's kind of arbitrary. We haven't really gotten to examples where it's quite like that. But ideal gases, again, are gases that behave exactly according to those parts of the kinetic and molecular theory that we've learned before. All right, let's go and see how this is applied. So example 1, a sample of hydrogen gas has a volume of 8.56 liters and a temperature of 0 degrees Celsius and a pressure of 1.5 atm. Determine the number of moles of hydrogen molecules present in this gas sample. All right, now what makes this problem something that you can maybe potentially get messed up with is the fact that there's so many numbers and there's already a lot of gas laws that you may have learned. So the most important thing is to acknowledge that it's asking for the number of moles. Oopsies. That's a big clue here because the number of moles tends to be something that, not always, but a lot of times, probably about 60-70% of the time, is going to be related to the ideal gas law. Why is that? Because remember, the ideal gas law, this formula of PV equals nRT, involves a value that includes mole amounts. And that mole amount, again, is pretty characteristic. So you basically would just set it up effectively however you need to that you can use and apply to solve for moles. Let's go and see what we're given. Based on the text here, a sample of hydrogen has a volume of this, so we have that value. Temperature of yada yada yada. We kind of have a mole temperature, right, because we're given a degree Celsius, but that should be an easy conversion to Kelvin, so we'll do that. And then a pressure of 1.5 atm, which again comes from that, right? So it's a pressure. You're solving for n, which I've drawn an arrow to. Well, of the 5 parts, I have 3 of them given to me. But then don't forget R, right? That's that universal gas constant, that value you're supposed to memorize. All right, so let's do a quick conversion here. because we need to make sure that this guy has to be in Kelvin. So 0 degrees Celsius plus 273.15 degrees Celsius. That was pretty poorly aligned. 0 degrees Celsius plus that gives you 273.15. Because my significant figures ends at the ones place, this actually should just be around 273 Kelvin. All right, so that's how you convert between Celsius and Kelvin. So that value right there, 273K, we can now plug into the formula. So let's go make that happen. Pressure is 1.5 atm, right, atmospheres. Volume is 8.56 liters. That's equal to N, which we don't know yet. We're solving for that, times the gas constant of 0.08206 liters atmospheres per mole K. Again, that whole thing is something you have to know. Times this temperature that we just converted, which is going to be 273 K. All right, so at this point, you have to solve for the mole amount, and that's what this guy is right here. And then rearrange it, solve for N. N is going to equal to 0.573 moles. All right, so that's the number of moles of hydrogen molecules that are present in this gas sample. That's the first example. All right, let's go and take a look at another one. A NASA experiment requires you to occupy a 100-liter balloon with 50 grams of oxygen gas at a pressure of 1 atmosphere. What temperature in Celsius must the surrounding air be to maintain the appropriate pressure? All right, so this one again gives you a little bit less information, or at least seemingly, because let's go back to the original formula. You have PV equals nRT. And I know I can use this formula here because that's kind of the section we're learning about. But again, in other contexts, when you're trying this out on your own, make sure you try to focus on the fact that you always have this available as a potential option. So give this a shot even if you're not really sure what to do with some problems. Because what's important here is that you identify what you're given. We have a 100-liter balloon, so we know that we have a volume that we're working with. 50 grams of gas. Well, none of these are mass amounts, but remember, if you have a mass amount in the identity of something, then you know it's also going to be possible to get a mole amount. So we technically kind of have mole amount. We also have a pressure of 1 atmosphere that we have to put this in. So we basically have everything. We're solving for temperature, and of course the gas constant is always available. So once again, we pretty much have everything we need. We just got to make sure we put everything in an appropriate way. So let's go ahead and figure this out. First of all, the thing I have to deal with is this 50 grams of oxygen gas. 50.0 grams of oxygen. Remember, it's oxygen as a diatomic molecule. It's O2. Let's convert that into moles by applying the molar mass. That's going to be 32.00 grams. Remember, this is a very common issue where you only look at one oxygen and not double it. So sometimes you might put 16.00, but this is 32. And then you convert that into moles, so per 1 mole of O2, and you do a little bit of math. The result of this is 1.56 moles of O2 gas. Let's go and plug some numbers in to our big formula of PV equals nRT. P is 1.00 atm times 100 point liters. That's equal to a mole amount of 1.56 moles times this gas constant, which is always available to us with all of these units, liters, atmospheres per mole K, and then times T, which we don't know. All right, rearrange, do a little bit of math, and you get a temperature of 781. Number of sig figs here should be 3 because 3, 3, 3, and this again is infinite because it's a constant. That's 781, but of course the units here, based on the rearrangement, you'd end up getting K, right? Because that K is what's left over once you rearrange all the work. But again, that's not what the question is asking for. It's asking for this in Celsius. So to convert this into Celsius, you do 781 minus 273.15, and that should get you 507.85 out of your calculator. But of course, we have to do it according to significant figures since the ones place is the least precision here, and this is pretty much a constant with infinite sig figs. You round this to 508 degrees Celsius. And that's your ideal gas law. That'll do it.